Okay, so let's go back. It's like quite a long time before we started or we did. So last time when we were talking about algorithm for the following problem. So we had vertex covered. It's recorded. Okay. So input was G, K. Question was, does G has a vertex cover of size at most K, right? But the parameter we were thinking was K minus LP of G. Okay. So K minus value of LP of G. And we had this nice algorithm. So what algorithm it was? Algorithm was apply pre-processing rules to ensure that all half is the unique solution to LP of G, and then was pick up a vertex U, pick up an edge UV, and branch with U in one side and V in one side. Okay, and we analyzed this algorithm and we saw that, okay, definitely the branching factor is 2, okay, and depth was at most 2 times K minus LP of G, as in both branches measured dropped by half. And what was the measured mu of G? Basically K minus LP of G. Okay, so this gave us 2 to the power, this gave us the following algorithm. Okay, now after that, towards the end of our class, we started to talk about surplus and those kind of things. So today we will do what I call, let's call it surplus and LP branching. Okay, whatever you want to call it. Okay. So even if you are switched off up until now, or you don't remember anything, I mean, it's okay. So what is a surplus of a graph? So I need to define the notion of surplus of a graph. Okay. So to do that, I say let I be an independent set. Okay, I be an independent set. Okay, and then what I'm going to do is surplus of I is basically look at the size of the neighborhood minus size of the independent set, right? So if you have an independent set here and look at its neighborhood, so it's a size minus this. So notice that surplus of I could be both positive and negative, right? So for example, right here, if I look at this independent set and ask for a surplus, then what is the surplus of this set? Is like 1 minus 3, which is minus 2. So surplus could be negative. So what is surplus? Basically, surplus of an independent set is size of its neighborhood minus the cardinality of the independent set itself. And what is the surplus of G? Surplus of G is the following. Okay, it's max over all independent set. I is an independent set, right? So among all independent set, I'm not talking about maximal independent set, nothing. among all independent set. So notice that it is also includes one quantity that it includes is what? One quantity it includes is this is like do you see? For any vertex, look at this degree of V, right? A single vertex is an independent set. So this object surplus of G is like at least how much? Is that okay? Is this clear to everybody? Right? Like, do you follow what I said? That because a single vertex is also an independent set. So for a single vertex, this quantity will be what? For every vertex, it is its degree minus 1. And since we are taking maximum over all independent set, so the quantity, the surplus of a graph will at least be maximum degree minus 1. So this is something interesting about surplus. Okay. So do all of you understand the definition of surplus? What is the surplus of a graph? So what is the surplus of an independent set? It's the size of its neighborhood minus the size of itself. And what is the surplus of the graph? You take maximum over all independent set. Okay. Okay. So now here's my question to you people. Curious question. Let G be a graph such that LP of G have a unique such that LP of G has LP of G has all half as its unique solution. Okay. Question. What can we say about surplus of G? Can we say something about surplus of G for such graphs? Anybody? What do you think? Okay. Okay, so let's have some discussion just so that to get a hang of it. So where is? Hi, Sonak. Can you hear me?
Yes, sir.
Do you think it could be negative?
No,
Okay.
it has to be positive.
Okay. Why? So Sonak is saying surplus of G should be greater than or equal to 0. Am I right? Is that your claim, Sonak?
Yes.
How many of you agree with his claim? If you agree with his claim, can you put +1? I want you to understand this concept because I mean, this is a concept which is
Saket, you are on mute.
okay. I said that a lot of you agree with him, but there are still a lot of people who do not agree with him. Okay. So if surplus of G is negative, what can we do? Let's see if the people who do not answer. Okay, I have to. Hi, Prateek. Can you hear me?
Yes.
Look, it has nothing to do with whatever we did before, right? So you, even if by just definition, what would it imply? Definition, what would it imply if the surplus of G is negative?
Not sure. To think about it more.
Okay, so what's the definition of surplus of G? It's basically, so if, can I say this? If surplus of G is say less than or equal to 0, implies there exists an independent set, right? I, such that neighborhood of I minus I is negative. Just by definition. Is that okay?
Yeah.
Right? Because what is the definition of surplus of G? Notice, surplus of G is maximum over I, n of I minus I. So if, I think I'm writing something wrong. Sorry, this not be maximum. It should be minimum. Otherwise, it doesn't make sense. Okay? Okay, it is a minimum. Okay, so you take all these differences and you take minimum over each. Okay, so if surplus of G is negative, it means there exists an independent set I such that the cardinality of n of I minus I is less than 0. So what does this set will look like? So if I draw a picture,
There are isolated vertices.
There is a crown.
no, there's I. No, look, no. Let's not assume anything. All we said, what is our starting assumption? That G is a graph so that all half is a unique solution for LP of G. Am I right? So let's try to contradict that. Okay. So suppose I have I, and what we know is that neighborhood of I is less than cardinality of I. And this is the rest of the vertices. Okay. What can we do then? Notice, assign all this to 0, all this to 1, and all this to half. This is still a feasible solution. Do you agree? This assignment is also a feasible solution because by definition, I is an independent set. Look at any i's edge. This is covered because of this edge. This is covered because of this edge. This is covered because of 1 and half. And this is covered because all of them are half. Am I right?
Yes.
But what is its value? Right? In the beginning, all half was a unique solution. So suppose I has a size A, n of I has a size B, and C, which is like A plus B plus C is equal to n. So now in the beginning, we had a solution of size n by 2, like the LP value was equal to n by 2. Now what is this? Now I have, so in the beginning, we had A plus B plus C by 2. And now if you compare to the new solution, what is this? It is just B plus C by 2. Am I right? The new solution we have made. This is all half is a unique solution, and this is B plus C by 2. Okay. Now let's compare them. Okay. So how is A plus B plus C by 2 compares to B plus C by 2? Right. So if A plus B plus C by 2 was a optimum solution, this is just any solution, which implies that A plus B plus C by 2 is less than or equal to B plus C by 2. Right? Now, sorry. Right? So what are we getting from here? What does this tells us?
A less than B.
Is less than B.
A less than B. But what did we assume? That A is greater than B. Am I right?
Yes.
Can't we directly say it by looking at after assigning 0 to A, 1 to B, and C half to C? Can't we directly say it's a satisfying assignment and it's not a half solution, and hence it's a contradiction?
No. I mean, all I'm saying that there's an optimum solution whose value is half. But there could be a non-optimum solution, right? Assign every vertex 1. That's a feasible solution, right?
Yes.
No, but if we say all half is a unique solution, that means
I said
that
all half is a unique optimum solution, LP opt. Otherwise, we do not make any sense. I'm looking at LP, I'm solving a linear programming solution to this. I'm saying there is wall half is a unique solution to this LP. Like among 0, half, 1 integral solution, this is the unique optimum solution. You do not have any other optimum solution where of the same value, where some are assigned 0, some are assigned 1, and some are assigned half. Because if we had such a situation, we knew how to reduce my graph. Unique, okay, my mistake. Optimum solution, okay. Is that fine now? That is why I'm comparing with these two quantities. I said, look, A plus B plus C by 2 was a optimum LP solution, right? And now I'm able to give you a solution, which is like, still, it has ingredients of 0, 1, and a half, and its value is actually better than what you started with, right? So what does it tell us? That implies if this is strictly less than this, or I mean, all I can say is that this is definitely less than. So A should be less than or equal to B, or rather B has to be greater than or equal to A. Is that fine?
Yes.
Okay. But now notice, if B is greater than or equal to A, what is the meaning of this? But even if suppose B equal to A, what happens then? What did you achieve if B equal to A? If B is equal to A, what did you achieve?
surplus equal to 0.
Yeah, but if all half was a unique optimum LP solution, you are able to get another LP solution of same value, which is not all half.
Correct.
Right? So it implies that in fact, if G has all half as unique LP opt, then surplus of my graph is greater than or equal to 1. Is that fine with everybody? So surplus and LP are related to each other in this way, right? So if you take all half as unique solution, look at the combinatorial property you have. There is no independent set in that graph, okay, whose neighborhood is at most equal to this. You get my point? So what are we saying after this? After this saying, or look at this nice combinatorial fact. If, meaning, Sriram, I don't get it. What are you saying?
Yeah. Why surplus is greater than or equal to 1? Why is it not equal to greater than half?
Surplus is a integral quantity.
Okay. Yeah, sure. Okay, sir. Yeah.
Surplus is number of independent set, size of neighborhood of I minus I. Okay. So what's the combinatorial fact? If all half is the unique LP solution, okay, if all half is the unique LP solution to G, then surplus of G is greater than or equal to 1. Okay, is that fine? This is what we proved. Okay. Now, what I want to do for next, want to understand graphs with surplus of G equal to 1, right? I want to understand what are those graphs with surplus of G is exactly equal to 1. Can we do something? Like, so notice that up until now, whatever reduction rule we have told to you is that they helped us achieve surplus to be greater than or equal to 1. Now, I want to tell myself that even if the graph has surplus of G is exactly equal to 1, we might be able to apply some reduction rule. Is that fine? So that is my goal. Okay. So my goal is to, what is my goal? My goal is to apply reduction rule to ensure that surplus of G is at least 2. So that is my goal. Okay. So I'm going to apply. So this is our algorithm's outline. So what is our outline of our algorithm will be the following. First, pre-process to get all half as unique LP solution. Okay. So once we will reach this, what we know? We know that surplus of G is at least 1. Okay. Now then I will check. Is surplus of G equal to 1? Okay. I will check. So if yes, apply reduction rule. Okay. And the third will be branch. Okay. So before we branch and branch will be simply pick up a vertex, and in one branch it will be G minus V you include in the solution and decrease your parameter by 1. In other branch you delete V and its neighborhood and you decrease your parameter by this, right? Because in any vertex cover, either vertex will go or one of its neighbor. That's all. So this is our algorithm. So up until now, we have understood the step 1. Okay. Now we have to understand the step 2. Okay. And then we will analyze. But there are 2 questions. How do we test? Okay. So let's write down our questions and let's try to answer question number 1. Okay. How do we test whether surplus of G is equal to 1? That's question 1. Question number 2, if answer to question number 1 is yes, what reduction rule we will apply? Okay. So first let's try to answer question number 2. Okay. And then the final question is, how does branching improve when surplus of G is greater than or equal to 2? Okay. So there are 3 questions. So let's try to first address question number 2. Okay. 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 So remember degree 2 reduction rule? What is this vertex? What is the surplus of this vertex?
1.
Exactly. So
1.
Exactly. Right? What is the surplus of this vertex? This is both one of the most simplest example of surplus 1 independent set. Am I right? Okay. What was the reduction rule for this surplus? For this, if we had this degree 2 reduction rule, what did we do?
We fold.
Hmm?
We fold by Z.
In the case 2, what did we do?
In case 2, we fold, right?
In case 2, we fold.
In case 2, we take the neighbors inverted.
Exactly. In the case 2, all we did is we deleted G minus YZ. No, G minus XYZ we deleted and we dropped K minus 2. Basically, we decided to pick this vertex and this vertex in this. Am I right? So this is one case. And in this case, if you recall correctly, what we did was folding. Okay, so what was folding? You basically, you deleted X, right? You made Yz adjacent to any vertex that Y or Z is adjacent to, right? And what else did we do here? So we got this graph G prime and we deleted K minus 1, right? This is what we did. So this is the simplest example of surplus one reduction rule applied, right? Now, what are we going to do is going to apply rules for surplus for which, I mean, these kind of will act as a basis for our understanding or basis of what you wish to do. Okay, is that fine? Okay. So by looking at these two things, remember when we were trying to make a branching rule, what did we say? Either from looking at these two, what can you say about, like, what can you say about X and Yj as a set? In any optimum vertex covered, either it contains Yj, there exists an optimum vertex cover that either contains Yz or X. Is that okay? Because if you pick either one of Y, then it is better to take other one, still it will do the same job, right? So we have used this fact. So what did we prove? That we proved the fact that, okay, so this is a observation we had. There exists an optimum vertex covered that either contains X or Y comma Z. Okay, you get my point? Is everybody okay with this observation? Look, in the case 2, we know there exists an optimum vertex cover that contains Yz, that we already know. In the case 1, okay, if your optimum vertex cover has to contain either X, out of XY, he has to contain one thing. From XZ, he has to contain at least one. So if he contains 1, then we are good. That is exactly. But if he picks up 2, then why do you want to take X? Then you take Y. It will do much better job than what X can do. So this is why we can assume that there always exists an optimum vertex cover that either contains X or YZ. Okay. Okay. So now let's take this. So now we are going to have a, so this is our independent set. Okay, for regions unknown to me, I'm going to call it Z. I'm going to call it Z, and I'm going to call it neighborhood of Z. Okay, neighborhood of Z. And what is the property of this? Cardinality of neighborhood of Z is equal to cardinality of Z plus 1, because they are surplus one set. Okay. Now, what are the potential two cases we could think of? What would be the like, you understand my point? Like, we have this case 1 and case 2, right? What could be the potential case 2 here? What can you like, and what could be potential case 1 here? Like, what will be the mimic? If you have to mimic it in this case, what it should be?
There is an edge between two vertices in J. Or not.
Excellent. Okay. So you are saying case 1 should be like, let's say, yeah, is.
I have one question. Are we still assuming that G has a unique LP solution?
Yes, Yes.
Okay. Okay.
We are always like look, I told you, right, where we are in the step of the algorithm. We are in the following step of the algorithm. First is done. We are here. So this is why I wrote the outline of the algorithm, that when we reach case 2 or the step 2, we have already performed case 1 or the step 1 fully. Okay. 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 So taking at what Sonak was saying is that, look, either n of z, this is an independent set, okay, or this is not an independent set. Okay, it means there's an edge between some vertex. Am I right, Sona? This is what you meant?
Yes.
Okay. So now let's, but yeah, so we will, this is how we will divide the case into. But before, let's prove a very nice observation. What's our observation? Is the following. Let G be a graph, okay, and surplus of G is at least 1, okay, and let G be, let Z be an independent set of surplus 1, okay, then there exists an optimum solution that either contains Z or n of Z. Okay, let's prove this. Okay. And what is the size of n of Z? Is this. So what happens otherwise? Otherwise, what happens is that you're going to pick up some solution from here. Am I right? And you're going to pick up some vertices from here. Okay? Is that fine? Suppose this size is total size is A, and this total size is basically, then we know it is A plus 1. And now suppose you have picked up some X number of vertices from Z and say some Y number of vertices from N of Z in the vertex cover. So what you have picked up? You have picked up X and you have picked up Y. Now tell me, what is the Y is at least how much?
A minus X.
Hmm?
A minus X.
Why? Look at this set of vertices that you did not pick. This. You have to pick all its neighbors, right? Am I right? If you did not pick some set of vertices, you have to pick all its neighbors, right? Where are its neighbors? And what is the size of its neighborhood of this pink set? What is the size of the neighborhood of pink set? This graph surplus of G is at least 1, right? So if this is, what is the size of this pink set? Y is at least A minus X plus 1. Because for every independent set, it says it has at least one more neighbor. So Y is at least A minus X plus 1. Okay. So how many vertices did you pick in total then? Then you definitely picked at least X plus Y, which is at least X plus A minus X plus 1, which is at least A plus 1 vertices. Am I right? If that is the case, why not pick whole of neighborhood of Z? Because that will do more job than picking partially from here, partially from there, right? So in this case, right, which implies it is better to pick n of Z, right? And hence what we have shown that either there exists an optimum solution that contains Z or n of Z. Is that fine with everybody?
Yes.
Okay. Now, does it prove case 2 now? Does it give you a reduction rule for case 2? Does it give you a case 2? I know that there exists an optimum solution that either contains Z or contains neighborhood of Z. Am I right? Either this or that. But so in the second case, what does it imply?
It has to contain neighborhood of Z because there is an
There cannot be an optimum solution. There cannot be an optimum solution, right? That doesn't contain a some vertex of this. Then if it does, then why don't I take that independent set that contains every vertex of that? Am I right? So doesn't that provide a reduction rule? Right? So the case 2, what is that? The case 2 is a reduction rule. What is the reduction rule? G minus closed neighborhood of I, right? K minus neighborhood of I. Is that fine? This is exactly like triangle case, which is easy to analyze, but that argument can be moved to even these kind of cases. Okay. Okay, so the reason why I'm teaching you this class, it is because for you to understand how do people start from basic things and then start to push new things, find new structures and design better algorithms. Okay. Okay, so this is great. How can I handle case 1? What is the great property of case 1? That neighborhood of Z is
Independent.
yes. So what should we do? Okay. Actually, folding comes from here. This is what we'll do. Case 1, fold. So what is a fold operation? It's very simple. G minus Z, first you do, so delete Z, plus add a vertex called V neighborhood of Z. This is my vertex. Add like basically Z minus neighborhood of Z. Add a vertex V in Z and make it adjacent to every vertex n of Z was adjacent to in G except a vertex in I. Is that fine? So for example, if we had, say for example, this is an example. This is a bad example. Let me draw better for you. Because both Z and NZ are independent, then what I'm going to get? You're going to delete this set of vertices, delete this set of vertices, and introduce a single vertex for this. And it is adjacent to 1, 2, 3. So maybe to everybody. Like, so this guy is representative of this. So whichever this vertex was adjacent to here, this guy is adjacent to. Whichever this vertex was adjacent to, he was. So this is basically a folding operation. This is what is called folding operation. Okay. So whatever I taught you before was a folding of a single vertex. And what is happening now is a folding of a set. Okay. Now, so what's our reduction rule? So reduction rule is very simple. You construct G prime, and it is K minus Z. Okay. So we have to show that G comma K is a yes instance if and only if G prime minus K minus Z is a yes instance. Look at the forward direction. Okay. What we know, there exists an optimum solution that contains either Z or n of Z. Okay. So look at the case when it contains Z. Then what will we do? Then I claim to you, say S, then S minus Z is a vertex covered of G prime, right? Why? Because look at this. Right? So in this case, what we know that S is that vertex cover that contains these, and it does not contain these, right? So in this case, what is the role of the black guy? It can only cover all the edges that is adjacent to the red guys, and anyway red guys are not there. So every edge that is adjacent here, like adjacent, all these edges, that is being taken care by vertices, which is here. And what is these vertices? This is precisely S minus Z, right? So these vertices are able to take care of everything here. So this is what happens when S minus Z is a vertex cover of G. Now, what else can happen is that n of Z is a subset of S. Then what will we do? We'll delete S of n of Z and add what? V n of Z. Right? This is what we added, right? Yeah. Yeah, we call it V of n of Z. Now, what is its size? So look, we know that the neighborhood of Z is equal to mod Z plus 1. So you deleted mod Z plus 1 and added one extra vertices. So that takes care of the fact that the size is K minus Z. Okay. Now, why did the vertex cover in this case? Well, you know that if these guys are there, I mean, this is very simple, right? Whatever these vertices could do, a single fat vertex can do also, and which you have anyway included in the solution. So all the crossing edges that this pink vertices could take care, that single V and J can take care. So you would have taken that, and every other vertices was only taking care of the graph induced on minus n of Z. So that is being taken. So this is exactly the argument we made when we were doing folding for degree 2 vertices. Okay. What about the reverse direction? Reverse direction is also easy. Okay. Either V NZ is in your S prime or V NZ is not in your S prime. Okay. So look at here, this is your V NZ and this is your graph. And there are lots of cross edges. Right. Now, suppose you are not in the solution. It means all its neighbors here are in the solution. So if you trace back and replace this x with this x with the corresponding n of z and corresponding z corresponding this side, then you know that all these edges are taken care of, and n of z is anyway independent set. So what is not taken care? So only thing which is not taken care are the edges here, and for that, what will you do? You do S prime union Z. And what is its size? Its size is K minus Z plus mod Z, which is equal to K, right? At most this, so at most this, right? And this takes care of all the edges in G, original G. Or otherwise, you do pick X in your solution. Okay. If you do pick X, then also we are good. Why we are good? Let's see. Okay. Now, suppose look at this fat vertex. Now, suppose we have included this vertex in the solution. So now what will I do? Then I know that if I have included this, no, if we have not, or did I tell something wrong here? No, this is fine when X was not in. But now I know this guy is included in the solution. So what I'm going to do, when I'm going to do this, I will tell, okay, fine. Look at S prime, you remove V of NZ and add N of Z, right? So what is its size? It is K minus mod Z minus 1 plus mod Z plus 1, which is at most K plus 1. So at most K, sorry. Right? Mod Z will get cancelled, minus 1 plus 1 will get cancelled. Now, what about edges? Well, I mean, by adding this, whatever this vertex could do, right? Whatever this green vertex could do, N of Z could do. And also by introducing Z, which only have edges to N of Z, you are also able to cover those edges with N of Z. So in both cases, you are able to, if in the reduced graph, you have a solution of size K minus cardinal TZ, you can trace back to a solution of size K in the original instance, right? So this implies that this reduction rule is, what do you call, valid. And we can make sure that if we are able to find a surplus set of, if a surplus set of surplus, a set, independent set of surplus 1, then we can apply our reduction rule, okay? So what does this imply? That if that we can move to branch stage. So what are we going to do? We are going to pre-process, get all half a unique solution. What I have not taught you, how to check whether surplus of G is 1. I will come to that. But if I did give you a set, you can apply the reduction rule, right? So what happens when 1 and 2 is not there? Then what is the surplus of this graph here? When you reach here, what is the surplus of this graph? Here. What is the surplus of G here?
At least 2.
At least 2, right? And that is the stage when we branch. And it is very hard to make a reduction rule for surplus G equal to 2. Why? Because this is exactly like when a vertex has degree, how much? 3.
3.
Right? So, yeah. Okay. But before, so what I have done now, I have answered question number 2. If we are able to find a set whose surplus of G is 1, like set whose surplus is 1, an independent set, then we can perform a reduction rule. And the reduction rule is very simple. Look at this independent set, look at its neighborhood. If the neighborhood of Z contains any edge, take everything in that set, delete both of them from the graph and reduce the size accordingly. If it does not, then you apply the folding operation, right? So it is a very, very powerful operation, okay? So now when we branch, so let me go to the question number 3, which we tried to do last time, but it was like very badly done. So let me do it again. Okay. So now we are in the step when surplus of G is equal to, greater than equal to 2. And we just pick up any vertex V and we are branching into what? In one side, it is G minus V, K minus 1. In another side, it is V, N minus V, K minus N of V. Okay. Let me do the second side and show to you what grade we are able to achieve this in this case. Okay. So now what happens is that, so we need to show, so suppose this is my graph G prime, I need to show to you mu of G prime is at least 1. So if the measure has dropped at least by 1 in this case, and then we will analyze in the left-hand side and say measure has dropped at least by half. Okay. So let's try to understand. So to understand what is mu of G prime is, I am to first understanding what is LP of G prime is. Okay. Now, what is LP of G prime? So basically, let's try to understand what is LP of G prime is. From LP of G, what are we? So look at this graph, right? So this is V, this is N of V, and this is your G prime is this. Okay. So now what are we going to do? So what was the property of LP of G? All half was a unique solution. Now what I'm going to show to this, okay, fine. Let's suppose, and G prime, let's divide them into, okay, and suppose X prime is an optimal LP of G prime. And what does this? This is say V0 with respect to X prime. Means X prime assigns these vertices a 0. And what does this assigns? V1 with respect to X prime. What are these assigns? V0.5 with respect to X prime. Okay. So now, what can we say? What is an LP of G in terms of LP of G? So notice, I can say, look, for LP of G prime, first from LP of G, let's subtract what? Whatever the value you had assigned to V and N of U. But you knew that LP of G, all half was a unique optimum solution. So I can just write it down. It is minus half of the following set. V union, is it V or U? I don't know what I did. Yeah, it's V. Okay. Is that fine? Now, what happens? Now, everybody had got half. But now, you are going to add plus that this V1 X prime initially were assigned half. Now they have been assigned how much? By 1. So this is like you have increased by value this. But what happened to V0 X prime? With respect to G, they were assigned half, but now they have been assigned 0. So you subtract. Is that fine? So is LP of G prime, if I'm trying to write in terms of LP of G, what happens? So I took LP of G. I said, okay, we deleted this set of vertices. Everybody was assigned half uniquely. So let's just delete the contribution of this. Everybody else remains the same. What are other changes happening? There are some vertices which I assigned half, but the new LP solution has assigned 1. So all these people are contributing at least plus half. But there are some people whom I have assigned half, but new LP solution has assigned 0. Let's remove their contribution. So this is what the LP of G prime. Is that fine with everybody? Okay. Okay, that's excellent. That's fine. If people are following, I'm happy. Now, what I want to do is that notice that what is the property of V and V0 X prime? What can you say about V and V0 X prime? Is V0 X prime independent set?
Yes.
Okay. Is V0 union V0 X prime union V independent set? Because look, V does not have neighbor in V0 X prime because all its neighbors are N of V. Okay. So let's call capital Z in terms of Z. Let's see. It's V union V0 X prime. And what is the property of Z? This is an independent set. Am I right? So what I want to write, like, because look, I want to somehow bring surplus in my this thing, right? So what should I do? I said, okay, fine. Let me get an independent set and let me get its neighborhood and let's see what happens. Okay. So this becomes LP of G is minus half of V minus half of VG prime. So can I say this is minus half of Z? Is that fine? And rest, let's leave it up. Okay. And now I leave minus half of NV, I leave it. And what I leave plus half of V1 X prime. This much, let's leave it for now. Okay. Now notice, please tell me where is the neighborhood of Z is. Where is your neighborhood of Z is contained inside? Where is the neighbor of V contained in?
Neighbor of V.
Excellent. And where is the neighbor of V0 X prime contained in?
V1 X prime.
Correct. So what can we say about this? This is at least
Z plus 1.
Z plus 1. Here's my Z, and here are something that's all its neighborhood is contained inside this set. And what do you know about Z and N of Z? What is the surplus of this graph? What is the surplus of G?
At least 2.
So if the N of Z itself is plus 2 larger than Z, then this, which might contain more vertices, is also this, no? You get my point? Like this itself, which is neighborhood of Z, is 2 larger than Z. Right? So anything more if is here or here, it can only make this set larger. So I can definitely say this object is greater than or equal to cardinality of Z plus 2. Right? That's all that I need for now. Okay. Now, having said that, having observed that now let's go back and try to understand our measure. So what is our measure? The changes I wanted to study, mu of G minus mu of G prime. And what is this? K minus LP of G. And what is this? K minus N of V minus LP of G prime. Right? Is that okay with everybody? This is, I just wrote definition. So K minus LP of G minus K plus N of V minus minus plus LP of G prime. Is that okay with everybody? Right? Now, this K and this K will get cancelled. Okay. And now let's write down whatever we wrote for LP of G prime. Okay. So what was the LP of G prime? Wrote LP of G prime was this quantity. Right? LP of G prime is LP of G minus this, plus this. Right? So let's go back and write it down. So what was LP of G prime? Can someone tell me? It is LP of G minus half of Z. Right? And what else was there? Minus half of NV. What else is there? Plus half of V1 X prime. Plus what was that? So this is LP of G prime we wrote. And what is this? NV plus LP of G. So what will get cancelled now?
This is minus LP.
Minus LP of G.
Oh, I'm sorry. Excellent. At least people are away. At least this much I can cancel, no? Okay. Okay. Now, okay. Half V1 x prime plus n of V, right? Minus half of Z. Is that fine? And what is this quantity? At least right? Look here, we did this computation. No? So I'm using exactly this because this contains the neighborhood of the Z, the independent set we created, containing V and V0 x prime. Okay, are we done now? What is this then? This is equal to half of mod Z plus 1, half of mod Z. This gets cancelled. This is equal to 1. Excellent. So surplus is, if we had a higher surplus, what will happen then? Will we get better factor? Yes. If we had a high, look at the same analysis. Suppose if I knew the surplus of graph is 5, then I can replace this with cardinality of Z plus 5. Then I will get 5 by 2 minus half or whatever. Yeah, that is the kind of, because everything else will get cancelled. So basically, this branch, if you just do nothing, do the same analysis. So the decrease is surplus of G divided by 2. Right? Because I could have written this. I could have written rather than plus 2, what can I write? This is surplus of G. I could have replaced this 2 with surplus of G and made this analysis. Now, okay. So in this case, this is what happens. Okay. Now look at the left side case. This case we have handled several times, right? So I will not do it again. This side, because all we care about in this side is that it drops by half, right? And this we have done even when we were doing half comma half branching. It's exactly like that. So you can't drop by 1, right? You can't drop by 1 because if you drop by 1, you can say, hey, all half is not a unique solution, right? So you drop maximum by half. You can't, if you drop just by 0, that's great for us. So you just drop by half and you get half from there. So do this for yourself. This is a good exercise. Try yourself. Okay. Okay. And you know, surplus has played such a critical role in theory of matching. That's very hard to underscore its importance. So there's a book by Lovers and Plummer about matching theory. Okay. There's a chapter where they have used this surplus of a graph very critically, and they also derive a polynomial time algorithm to compute surplus of a G. Okay. Okay, using some linear programming. But so I have answered this, right? First, if we have a surplus 1 set, then we know how to reduce it. Second, if the surplus of my graph is at least 2, then I get 1 comma half comma 1 branching, which is like 2.618, right? So this leads to 2.618 K minus LP of G. Okay. Okay. But another important question is, how do we test the surplus of G is equal to 1? Is that fine? So let's spend another 20-25 minutes trying to answer that question. At least in our case, I still don't, I don't remember the proof for computing a graph of minimum, like computing the minimum surplus of a graph. That also can be computed in polytime. So it's not in some, but I don't know how to compute that. Okay, I don't remember. But let me tell you how to compute. So question is, how to test whether surplus of G is equal to 1. Okay. So first thing, all half unique solution implies what? Surplus of G is at least 1. This much we know. But all we want, is it at least 2 or is equal to 1? Right? That's what we want to distinguish between. Okay. So let's try to check first. Is there a surplus 1 set? So I want to have the first. Oh no. Okay. Okay. So I want to first test and then we will move to the other testing. So test, does there exist Z an independent set such that first neighborhood of Z is equal to mod Z plus 1 and neighborhood of Z is not independent. Okay. What do you think could be the test? So let's ask ourselves following thing. Suppose such a set exists and then, okay, so let me, okay, I don't think it's very intuitive. So let me tell you what happens. Okay. But it's very beautiful. So here's the Z. Okay. And here is, suppose this is neighborhood of Z is mod Z plus 1. And here is, suppose such a set exists. Okay. Ask yourself that suppose I assign this to 1 and this 1. I fix that, let's assign this edge UB and both its endpoints 1. How much LP can change? Hmm?
1.
Okay, so rather, let's see. Okay, okay, let's rather say, suppose we had such a set. Okay, and let's try to see if I assign all these guys to be 0, all these guys to be 1. Okay, and the rest I just assign to be half. If we have such a set, what is the LP value now? how much will the LP value change?
Half.
Just by half, because I'm always in the case that all half is a unique solution, or I know that LP of G is at least 1. I'm trying to distinguish between 1 and 2, right? So what happens here? Okay. So now notice what is the property of this edge. Notice the property of this edge is, or whatever it is. So if I had such a situation and then I assign every vertex in this as 1, okay, and 0 and half, I see that this new LP solution, right? New LP solution, let's call it, this is an X prime, and X prime is the new assignment, and X is the old assignment, okay? And let's say, just to, because we need this, weight of X is like you sum the weight. So what is this? Weight of X is a value of LP with respect to X, and weight of X prime is value of LP with respect to assignment X prime. So what do you know? Weight of X prime is equal to weight of X plus half, right? So what we learned? We learned that if there exists an independent set such that this property happens, n of z is mod z of plus 1, and n of z is not an independent set, then what we are able to say, then there exists, then we can come up with, like, then something interesting happens. What is interesting happens? If you look at the set Z, so n of z, you assign it to 1, you assign it to 0, and remaining half, then your LP value only increases by half. Okay. So what happens is that when the converse of this statement is true, you can actually create such a set Z. Okay. So what I mean by this is that actually following statement is true. Okay. So what you have a statement, there exists a set Z, okay, such that surplus of Z equal to 1, n of Z is not independent, okay. Okay. If and only if, okay, there is an edge u comma v in E such that solving linear programming of G with xu equal to 1, xv equal to 1 results in a solution, okay, with value exactly half greater than the original LPV, right? So what I'm saying to you, you solve your original LP. Now you constrain your LP. You pick up an edge and you assign them to be 1, 1 and say, now solve this. This LP value just changed by half. Then I'm telling you there is a set Z with this property, right? So what does this tells us? Okay, so this will give us algorithm. If I prove this, then what I will do, I will take an edge, assign both of these as 1, means what? You delete this from the graph, solve the LP value of them, the remaining guy. Whatever LP value comes, just add this. Okay, 1, 1. So you got a value. You solve LP of G, you check the difference. Okay, if they only differ by half, then I'm telling you there exists a surplus 1 independent set, and we can construct that. Okay, and I will show you how. So this provides us a polynomial time algorithm to find a set Z whose surplus is 1 and its neighborhood contains an edge. So we have to first prove this. Okay, so let's prove the reverse direction, because forward direction we just saw. That is what the motivation was. Okay, so what is the proof? Suppose there exists an edge UV, and what is the property? Such that weight of x prime is weight of x plus half, okay, where x is the solution to original LP and x prime is the solution to LP when LP with xu equal to xv equal to 1. Sorry, x prime u equal to x prime v equal to 1. So do you understand what I'm trying to say? I'm trying to say that look at an edge in your graph. Look at your LP of a graph. Okay. So here your graph G. You computed some LP value of this. Okay. You pick up an edge. You pick up an edge UV in this graph. Delete it UV from the graph. Okay. Look at G minus UV. Compute its LP value. Okay. Compute its LP value. Now add +2 to this and look at the LP of G and this LP. Do they differ by half only? If they differ by just half, then I'm telling you that I can find a set Z which is an independent set. Neighborhood Z contains an edge and blah blah property holds. Okay, is the statement clear to everybody?
Yes.
Okay. So, okay. So what is our Z? Z is very simple. Okay. So basically, I have G. Here also I have G, and here is UV and UV, and what is that? X prime of U equal to 1, X prime of V equal to 1. With this constraint, I have solved the linear programming of this. Okay. Now, I'm saying let's consider Z equal to V0 of X prime. Okay. So what is Z? Is a V0 of X prime. Okay. First claim. So what we have to show about Z? So first of all, Z is independent because it is V0 X prime. Second, I will show that N of Z contains UV, okay, which will imply that N of Z contains an edge. And then I will show to you that Y side of NZ and Z exactly differs by 1. Okay. So suppose I first show you that U belongs to neighborhood of Z and V belongs to neighborhood of Z. It's not at all clear that this will happen. But suppose this happens, right? So in this graph, if U is not neighborhood of Z, so what happens then? So let's say this is V0 of X prime, and this is V1 of X prime, and this is rest. Right? And suppose U belongs to here. No, what is this? U belongs here by definition. Okay. Now look at the neighborhood of this guy. So this is your neighborhood. Okay. Now, what is the property of U? All its neighbors are either here or here. It does not have neighbor in V0 X prime because otherwise there's nothing to show. That then we have already shown that U belongs to neighborhood of Z. So what is the green portion? So this green portion is neighborhood of Z. Z is this. Then what you know about U? All the guys here. What is this value? Please tell me, what is the value of all these guys? What is the value assigned to the neighbors of U? Hello?
We removed U and V from the graph, right? So
No,
you should be
that-
outside
no,
U and X.
no, I don't think of them as removing. That was just for the solving. Think of them that we have assigned 1 to them.
Okay.
I have solved my LP by assigning 1 to them. Okay, so they are just 1. I have not changed my graph. It's just assigned 1. Where are these neighbors? Look, if all the neighbors of, if you had any neighbor in V0, what will be the nice thing about this? Then U is a neighborhood of Z. But now, because of this, what are the values the neighbors of U takes? It takes either the 1 or it takes half. Am I right? Is that okay? Okay. Now, we had X prime. Now I'm going to make X double prime. What is X double prime? I'm saying assign U to half. Now, please tell me, and like, what is X prime, X double prime? Assign U to half, and for others, take the same value. Now, what happens? Please, is this a feasible solution?
Yes.
Because nothing has changed. But what happened then? So look, X to X prime, look, here's an X prime, and here's the weight of X, which is an optimum LP. What is the weight of X prime? Is this. What is the weight of X prime? Is weight of X plus half. What is the weight of X double prime? What is the weight of X?
W.
Weight of X. Is that fine? Because U was assigned 1. Now I reassigned U to half. And still it is a feasible solution. What is its weight?
Yes.
Then what does it contradict, guys? Does it contradict something? What is the value of V in this assignment? X double prime. Look at this. This is how it was, no? U and V, right? And what is the property? Weight of X prime is equal to weight of X plus half. And what is the weight of X double prime? Is weight of X prime minus half. So this is equal to weight of X. Is that fine? But now I have another vertex which has been assigned 1. So all half was not a unique solution. That's all that had happened. Is that okay with all of you? Or completely confused? Sonak, are you confused? How many of you have followed and how many of you have not followed? Is anyone who has not followed? Okay, fine. Okay, so all we have achieved, this contradicts the fact that all half was the unique solution. So this way you can show that both U and V belongs to neighborhood of Z. Okay, this is how you can show that U and V belongs to the neighborhood of Z. Okay, so now what we have been able to achieve? We are able to achieve, here is the Z, neighborhood of Z contains an edge UV. So the only thing we need to show is, okay, and that's easy. Why it is easy? Let's see why it is easy. Let's see why it is easy. Okay. So the weight of X prime is equal to what? Weight of x minus half of v0 x prime. These are the vertices who got reassigned, okay? Plus half times v1 x prime. And what we know about weight of x prime? What is this? This is equal to weight of x prime, weight of x minus half of cardinality of z plus half of neighborhood of z, but this is equal to weight of x plus half, right? And now from here you will get that n of z minus mod z equal to what is that? 1, which is surplus of z. Is that fine?
Yes.
Right? So what we have been able to show. So I already showed you the reverse direction. So to check whether graph contains a surplus one element or not, what we are going to do, we're just going to do the following thing. We pick up an edge, assign both of its values to 1, recompute the LP with this, forcing these two variables to set 1 and check its LP value. If its LP value only increases from the original by half, we can use this to find a surplus set of 1 with the property that the set contains at most set contains an edge. Okay. Now, finally, so you first do this, and when you assume that such a surplus set doesn't exist, you can prove something very similar. Okay. So here's another claim or lemma you can prove. Okay. G. So what is the property? That surplus of G is at least 1. So you have to assume this. Okay. So G contains a set Z such that surplus of Z equal to 1, and n of Z is an independent set. Okay. If and only if there exists a vertex U in V such that same kind of thing, LP vertex cover of G with XU equal to 0 results in a solution, okay, with value exactly half greater than the value of original LP. Is that fine? So what is it? So suppose you know that the surplus of G is at least 1. Surplus of G it doesn't contain a set Z whose surplus is 1 and its neighborhood contains an edge. Then our final test is, I want to test whether when all these three fails, I want to test, does there exist a set Z whose surplus is 1, okay, and it is independent. And that, how do we test? I said, okay, fine. Let me set a vertex to 0. Okay, let me assign a vertex to 0 and recompute its LP value. If this LP value is greater than, just increases by half with the previous LP, then we are done. Okay, so I will not give you proof for this. It is exactly like the same like this. So you can do the same thing just before like that. Okay. Yeah. So this is just a test to test whether the graph has a surplus 1 is equal to 1 or not. Okay. So all I wanted to tell you is that notice that in research, we start with very simple things, okay, like degree 1 reduction rule, degree 2 reduction rules, and then they mesmerize yourself, or then like they just become something more complex, much more difficult, or whatever you want to call. But the idea is, the seed of the idea just is there, like it's just there. I mean, so once you understand the value of surplus, you say, hey, what happens if the surplus of graph is greater than or equal to 2? Then, like the moment you come up with these kind of analysis, okay, this is the analysis which, like, I mean, we were trying to see how to improve the algorithm. Then we just came up with this kind of this analysis. I like this analysis, which I told you, right? In terms of surplus. Okay. So this was the discovery in some sense, like this 2-3 line of writing this into a different thing. Then I said, oh, this is an object if I can ensure that. Oh, but how does it even ensure for negative? Oh, that is already being ensured by all half being unique solution. Oh, then it becomes at least 1. Oh, for equal to 1, we know how to apply reduction rule, because this is exactly, because we somehow wanted to make sure that what is the analog of take a vertex like degree 3 branching, okay? And when you try to have that degree 3 branching analog, then this is the kind of things you start to get. You understand my point, right? So the moment you have this analysis, you understand the importance of surplus. The moment you understand the importance of surplus, you try to increase the surplus as much as you can. You are able to do 1, then you get to 2, and your analysis work. Now, only thing is, can I find a surplus 1 set? And then you play around with LPs and we already knew by combinatorial optimization that you can compute in poly time. So you just make it some slightly more combinatorial algorithm. Okay. So the main focus or main motive for you was to analyze and understand that simple things could be utilized and make sure that intuition pushes in the right direction to design a very, very intricate algorithms with much better running time or whatever you want to say. Okay. So that's all that I wanted to tell today. From tomorrow, we will move to a completely different topic. But again, with respect to vertex cover, most likely we will go on to do a little bit of FPT approximation and W hardness, and then move to some other topics in the book. Is that fine? So until you have a question, at least I'm done for the day.